The second type of chemical reaction out of the 5 are decomposition reactions. By nature of the word decomposition, we normally have to add heat or electricity or something to take a compound or a molecule, and then it breaks apart into components. It could be elements or it could be other compounds. So that implies that it's going to be an endothermic reaction. You need energy. So let's do some examples. The first one I have here is lead 2 hydroxide. So we need to write a formula, and you can always stop the video and do this. Lead is Pb. The Roman numeral 2 indicates the oxidation state of the metal, which is lead plus 2. Hydroxide. You look on the periodic table, you won't find it. It's on the back, on the chart I gave you. It is a polyatomic ion. So hydroxide is OH and has a -1 oxidation state. We crisscross the oxidation numbers. A 1 would go there, not a -1, just a 1, and the 2 would go there. That means we have now 2 negatives and 2 positives to make that balance. Since it's decomposition, we have a reaction taking place. Now, the easy way to do a decomposition reaction is you look at the formula and you decide what molecule or compound is very familiar that I could find in that. And when I look at this, I can see water there. Water's formula, you're familiar with H2O. However, it can also be written HOH. The H plus part is an acid. The OH minus part is a base. You put the two together and you get a neutralization. You get a neutral molecule called water. So the OH is right there. So we can put that over here, plus water. And if you want to write it as HOH, that's perfectly fine. So what's left over? Well, most decomposition reactions involve oxygen. Not all, but most of them. And they will end up with an oxide. So in this case, you're going to get lead oxide. Now, we don't assume anything with that subscript. That subscript refers to that formula. So we go here, we start fresh. We need oxidation numbers. Lead is +2, just like that side, and oxygen is -2. So when we crisscross 2 and 2, then simplify it empirically, so it's 1 and 1. That is the formula. Okay, so these are the correct formulas. If you want to write in water, it's +1 and then -2. Now we need to balance the equation. So to do that, we look at lead, there's 1 and there's 1. Remember, these are oxidation numbers, not amounts. Oxygen, there's 2. The 2 refers back here. And there are 2 here. Hydrogen, there are 2. And there are 2 there. So this equation is balanced. The only other thing we might want to add in is to show that it's endothermic. So we'd want to indicate where is the energy. And we said energy needs to be added in, so you'd actually put it over here. Energy would be added into this equation. So that's one example of a decomposition reaction. Let's try a second one. I have calcium carbonate. So again, we need to write the formula. Calcium, Ca. Carbonate is CO3. You look that up on the reference table. The oxidation numbers, +2, -2. So if we crisscross, it's 2 and 2. Simplify empirically to 1 and 1. So that is the formula. These are all solids, by the way. They're reagents. I find them in my chemical storeroom. Again, I have to add heat or electricity or something to get it to decompose. So I look at that formula, and again, I ask myself, what common molecule is in there that if I split it up, it will come out? And hopefully you can recognize carbon dioxide is in there, what we breathe out. So let's put that over here. What's left over, like I said the last time, is normally going to be an oxide. So we have calcium and oxygen. We put in all the oxidation numbers, +2, -2. And here we already know the formula for carbon dioxide, but if we wanted to put it in, this is +4 and that's -2. So again, we balance the equation by inspection. 1 calcium, 1 calcium. 1 carbon, 1 carbon. 3 oxygens on that side produce from 3 oxygens. And again, if we want to indicate that it's endothermic, the energy is actually a reactant. Let's do one more for practice. I have potassium chlorate. And the main idea, this is a chlorate. You could use any metal here, but we're going to pick potassium. So we write the formula. Potassium is K. Chlorate, you have to look it up on the polyatomic ion chart. Looks like this. The oxidation state of potassium is +1. For chlorate, it is -1. So the formula is done for us. And again, this is a solid. And we want to see what it turns into when we add heat or electricity. And a lot of times, scientists will use the delta sign for heat or electricity or energy being added in. Again, the question is, what common molecule is in there that can be decomposed? And I hope you can see there oxygen. Oxygen is a Hofbrinkel element, so it cannot exist by itself. It's written as O2. And what's left over? In this case, it's an exception to the rule. Normally we'd say there's an oxide, but in this case it's not an oxide, it's a chloride. So it would just be KCl. Put in the oxidation numbers. Potassium is +1, chlorine is -1 in this case. This would be 0 because it's no longer bonded. So by inspection, we have 1 potassium each. This is like an equal sign, remember. 1 chlorine each, but now we have a problem. We have 3 oxygens here and only 2 there. And 3 and 2 aren't going to jive unless you come up with a number like 6, because both can go into 6. So let's say that we need 6 oxygens. Here we'd have to put a 2 out front. That would give us 6, and we just need a 3 there. That would give us 6 oxygens. Since we changed this, however, now we need 2 potassiums, so we put a 2 there. That gives us 2 chlorines here, and this gives us 2 chlorines there. And that is the full equation. Again, it is endothermic, so we could add energy in here as a reactant.